Hello? Okay. Hello? Hello? Okay, so, I think I am live right now. I will start studying in a few minutes and just do some stuff. Okay. Oh, there are 2 viewers. I don't know why there are 2 viewers. I only sent this link to one thing. Okay. Let me do something really quickly before I don't know if anyone can hear me. I checked my audio and everything. So I should have done that to begin with. Oh, nice. Oh, there are 2 people concurrently viewing. Okay, I'm going to start now, I guess. For those of you who are watching, the 2 of you who are watching, I guess this is going to be like ASMR. I have not made a video with a script in a very long time. So all of this is going to be me reading my notes, preparing for my test tomorrow. And wait. Okay, so I did. Oh my gosh, we're up to 3. Okay, I guess 3 is a good number to start. I guess we'll start now. Hello everybody. Hi all 3 of you who are watching. It's time to start studying, and I will be talking through all of the reactions that I'm about to show you. I might get stuff wrong. I don't know how many of you watching this actually know what's happening in chemistry, but if you do and I make a mistake, you are free to correct me in the comments, and I will correct my mistake. Okay, so let's start. So I believe that this test will cover, so number 1, so there are going to be alkene additions. Number 2, there are going to be alkyne reactions. You can kind of say that these are going to be all kinds of reactions. I'm going to stop. And number 3, we have aromatic compounds. I think these are the 3. And while these are only 3 topics, there's a lot to them. So, okay, let's do this. So, all alkene addition reactions are going to follow. I feel like your jokes require an audience reaction. I agree, they do. They're too good to just be me talking to myself. Anyway. Yeah, I don't think I'll be able to make any more jokes after this, because this is all suffering from here. So, before we begin, I just want to say that okay, let's start with alkene additions, right? So, all of them are going to follow the same general trend, right? So, you have an alkene. It doesn't really matter what these things are. Remember that an alkene is a double bond between 2 carbons, right? And you have a sigma bond. This is the first bond that forms between any 2 carbons. And you have a pi bond. And I'm not going to talk about what those are that much. That's going into like the orbital geometry of this. And I don't feel like talking about that. But what we need to know is that these pi bonds are nucleophiles. This is a nucleophile. And I don't know how many people use this analogy. I use it. A lot of my friends don't for some reason, but I think it helps. So this nucleophile is like Spider-Man's web shooter, right? So, oh God. I know there is an artist watching this video, and they're gonna like come at my art skills, but Okay, just think of that as his hand, as Spider-Man's hand, right? And like he shoots the web, and it hits something. I don't know. I'll draw like this is the Green Goblin, right? Green Goblin. Tee. So this the point of that is this nucleophile kind of serves as a web shooter. It can attack something and draw it in, and this something, this target that it's attacking, is an electrophile. Right? It's more electron deficient, so it's going to have a positive charge, and your nucleophile is going to have a negative charge. And this makes sense if you think about it, because if bonds, these covalent bonds are just two electrons, right? 1 and 2. So because you have a double bond which has an extra pair of electrons in between the two carbons, you're going to be able to attack a more electron deficient, what do you want to call it? Do I want to call it a molecule? It can be a molecule, or it can be an atom. It can be anything. It's an electrophile. So that's what we call a nucleophilic attack. It performs an attack. I like to think of it that way because let's say we have something like, I don't know, we'll just say A and B. These things are bonded together. What you're going to get is this nucleophile attacking this A, which is presumably an electrophile. This bond will move here, give a lone pair to B, and what you're going to end up with is A here, B here, and remember that B has two lone pairs. And because this bond broke and these two electrons were used to form this bond between this carbon and this A, you're going to have a positive charge here, because now this side is electron deficient. And we have a nucleophile here now, B, positive charge A, that's an electrophile. It's going to attack here. And there you go. You're going to end up with this alkane with two groups. This is not really a... Thank you. My art is amazing. Thank you. And we're also up to 3 viewers. I don't know who... oh, now we're back down to 2. I have a bit of a delay between what I see here. Oh, we're back up to 3. Okay, anyway. Let me just check my Discord really quickly because for some reason my streaming mode is enabled. Okay, that's okay. Yeah, so this is not going to be like any other normal video where I actually, you know, am teaching it. This is me studying, so I might get stuff wrong. I probably will get stuff wrong. But anyway, let's talk about some alkene reactions. And so I have my notes here. There are 11 alkene reactions, and I like to think of these as like fight moves. So there are 11 different combos, fight combos that you can do for the character of alkenes. Okay, actually in our previous test we did the first 5, and so I'm tempted to just skip the first 5, but just for the sake of me knowing everything well, let's do all... how many would there be? 11. I just wrote that down. 11. Let's start with the first one, which is called Hydrohalogenation. Oh my god, Hydrogenation. We could have started with any of them, but I feel like this is the simplest one. So, in hydrogenation, you have an alkene, and the thing that you're adding across the pi bond, we call this adding across, well, your thing 1 and thing 2 that you're adding to these 2 carbons, is the hydrogen molecule. So you're adding a hydrogen to this side and a hydrogen to this side. And that makes a lot of sense if you think about it. So the way we would draw out this mechanism is you have your hydrogen-hydrogen bond, boom, boom. So you're going to start with this. And actually, you could draw this hydrogen here, but because this is organic chemistry, it's not really needed because it's attached to a carbon. That's just the rule of line angle structures. I think they're called line angle. I don't know. Then you have your hydrogen atom here. It's going to attack, and you're just going to end up with a normal this. So ideally, that's how it would work. However, but I actually just lied to you. I lied. This does not happen. This is not spontaneously going to happen. You need a catalyst to do this. You need a catalyst. And specifically, we're going to use palladium or sometimes platinum and C, which is carbon. Yeah, I'm sorry, I lied. I made a mistake. I thought. Yeah, so that was just a general formula. This is actually what happens. I promise you, I will be more in the swing of this in a few minutes. I just got off of a Zoom call, so I'm not really thinking about this that much. Let me just respond to something really quick. And take a look at this before I say something wrong. Yeah, okay. I do know what I'm talking about, kind of. So the way this is going to work is you're going to have, I don't know, let's make this blue. You're going to have a platinum metal surface, right? This is platinum. Palladium. I don't know my structures. Although I think platinum would work too. I just have PD here, so just for consistency, I'm going to use palladium. I don't have my periodic table in front of me, but I'm 99% sure that's palladium. And you're going to have your alkene look like this. So you're going to have your carbon here, carbons bonded together. They're going to be attached to the metal surface, and you're going to have the hydrogens. So we're fulfilling the octet rule over here. And another key thing to note here is, if you're in Gen Chem, you probably won't know this, but if you're in Orgo, you will. These have geometries to them. So these hydrogens are facing upwards, so we like to put them on a wedge. These hydrogens are going into the page, so we kind of put them on a dashed line. And that's going to be important because if you think about it, the bottom half of this molecule kind of is attached to this palladium surface. And so anything that gets added is not going to be able to attack from that bottom side, right? So just something to note here, because that's going to be important when we talk about a very, at least my professor really likes to talk about it, and hopefully yours does too, because it's important. We have our hydrogen bonds here, and what they're actually going to do is they're going to bond to the palladium surface as well. And what's going to happen here is now we can have this attack, this whole thing here that we showed before. So we need this surface here, this palladium surface, to get this reaction to happen. And so now we can have the attack from this pi bond to the hydrogen here once it's bonded to the palladium. And this will happen twice, once on this side, once on the other side, once that becomes electrophilic. And then you're going to end up with your end product. And this is pretty straightforward, right? But note that these attacks have to come from this bottom side. And the reason is they're bonded to the palladium. That's a key concept. They can only attack from the bottom. They can't attack from the top here. This is not going to happen. All of these orbitals are filled. And so what's going to happen is you're going to add to only one side. We call this the Syn Addition. of hydrogen. If you were to, say, have one attached to this side here, but a second one is attached to the top side, you would get the anti-addition. So syn and anti. We have to remember if these reactions are going to be syn or anti, and sometimes I guess you could, hi Steven. Steven's here. Oh, 5 concurrent. Who are the 5? I only put this in like 2. Who's watching this? I know Isabel's watching. I know Steven's watching. I don't know. Is George watching? I don't know, Okay, let's keep going. Okay, I promise you, I just spent way too long talking about this stupid reaction. It's literally just adding hydrogens. 99% of the time, like if you have this... Oh, that's not going to work. If you have this thing and you do this reaction, all you're going to do is remove the double bond. 99% of the time, that's what's going to happen. But it's good to know that. Okay, that's number 1. I promise you, I spent way too long on that. It gets easy. Well, not easier. That's the easiest one out of all of them. But I'll spend less time. This one's more straightforward. This one is electrophilic hydrohalogenation. Hydrohalogenation. Okay, so... Oh... Okay, MT is watching. I don't know who you are, and you just found this by random. Nice. And Ahmed, what's good, Ahmed? Okay, so hydrohalogenation just means we're adding hydrogen and a halogen, usually denoted as X in organic chemistry. So these are, fluorine, chlorine, bromine, iodine, or iodine. I don't know why they say iodine and not iodine when you have fluorine, chlorine, bromine. Could have made more sense that way. And there's one more, but we're not going to talk about it. It basically doesn't exist in organic chemistry. It's acetine. And we're adding hydrogen to one end of the alkene. Basically, hydrogen to one end, the halogen to the other. Okay, pretty straightforward. Now, here's a question, right? And I guess if you actually take organic chemistry, this is easy. But if you don't, it's interesting. Okay, so let's say that we have this alkene, hydrogen, methyl, and then this is ethyl, right? We know that we're going to add the by MT. Okay, that was random. Okay, so we know we're going to add H and X across the alkene. In this case, right? So in the previous cases, we saw symmetrical cases, so it doesn't really matter which side you add the H and H to. But in this case, is the hydrogen, or rather the halogen, I guess, we can do the halogen in green, is the halogen going to go to this carbon or this carbon? So that's an interesting question that you always have to ask yourself when you do these reactions. Sometimes you'll be asked to work backwards, so they'll give you the product and they want to know the reaction. But let's just do the forward mechanism for now. So just keep that in mind. So let's try out this reaction, and let's try to do it with the asymmetric alkene, right? So CH3. I'll use this as my example. I like this example. It's like anyone who I taught general chemistry to, you know that my favorite example is always going to be nitric acid with anything. It's just because it works for basically everything. Nitric and acetic acid are the two examples that I use. Also because they're the formulas that I remember the easiest. But now I know all the strong acid formulas. At least I think I do. So, okay, so in this case, we're going to have our nucleophile, the pi bond, attack the hydrogen, our electrophile. So this is just our general mechanism that we went over at the beginning, and we're going to get... Oh, there's no more double bond. CH3. And now the question is, are we adding the hydrogen to this side, question mark, or this side, question mark? Well, the key here is that remember that wherever you add the hydrogen, you're going to add a positive charge to the other end. So we could add the positive charge here, or we can add the positive charge here. And the trick is that remember that any carbon with a positive charge is a carbocation, a carbon with a positive charge. And carbocations favor the most stable position they're going to get. So if you think about it, between this carbon and this carbon, over here we have a 1, 2, 3 tertiary carbon. Over here we have a 1, 2 disubstituted carbon. This carbon is going to be favored. So we would rather have the positive charge here. Therefore, we're going to get the hydrogen here. And so whatever X we have is going to come to this side. So what we end up with, actually, is your X on the more substituted side. This should be CH3. And this is called the Markov-Nikov product. It's a long word. I guess that's the name of the guy who found this out. I don't know. Probably. It sounds Russian to me. Markovnik or German. I don't know. Anyone here who knows Russian or German want to confirm. Markov-Nikov. We're going to add this X, this halogen, to the more substituted side. So that answers that question. But what if you want to add this to the less substituted side? Then we're going to have to do a different kind of halogenation, which is the free radical. I'm just going to put HH. I don't want to write out the whole thing. Please don't make me. This happens when we have your HX with some kind of peroxide. So ROOR is the general formula for a peroxide. And before we deal with the actual alkene reaction, we have to do some reaction fun here. So first thing we note is that this bond is going to cleave between these two oxygens. And we have to represent that using fishhook arrows, indicating that one electron is moving at a time. And I think I have a video like that on my channel. So we're going to get RO, radical, OR, radical. It doesn't really matter what order you do them. But know that this radical here will be on the oxygen. Next, we're going to get this bond here broken. So it might be more accurate to do it like this. Right? So this HOR is going to form. We're going to get HOR. And this other electron will go to this halogen, and we're going to get the this radical here. Now, note that this is not the same thing as this. So over here, this halogen has two. We're removing 2 electrons at a time. This has a negative charge. Over here, this doesn't have a negative charge. What we're saying is that one electron is moving at a time. This actually has 7 electrons, which is why, actually, if you look at the periodic table, this is the atomic form of this element, whatever this is. And so we're going to end up with, let me draw our example here now. We're actually going to get this to cleave with a fishhook arrow. So one electron will go to one side and the other will go here. So in this case, we're going to, and if you don't know what this is, I think you should, watch a different video, because this is more complicated than, and this is higher up in the organic chemistry curriculum than fishhook arrows. Okay, so in this case, we're adding the halogen first. Which side will it add to? So in this case, we want to stabilize a lone electron, a radical. So will the radical be more stable here on this carbon, or here on this carbon? And of course, it's going to be this carbon. This is a tertiary carbon. It's more stable here. So we're going to leave the radical here and just add our X. I almost wrote bromine because bromine is the most common halogen and one of my personal favorites. I just said I have a favorite fucking halogen. I don't know if anyone except for chemists has one. And finally, we have, I believe we have our, I can't remember if it's this that cleaves or if it's this intermediate HOR that cleaves. I think it's this one because this one looks pretty stable. This one, it's also stable. Actually, no, this is not stable at all. This, oh God, someone in the comments help me out. This one will dissociate completely, but what's going to happen is you're going to get this thing. This is a very bizarre way to draw curved arrows. Please don't do that on your actual tests. But in essence, this is going to add the halogen to the less substituted side. And this should not be a single bond. This should be a single bond. It should not be a double bond. And the X is added here. There's a hydrogen. So this will get you the this is called anti-Markovnikov because we're adding the halogen to the less substituted side. Okay. This is taking a really long time. If I stay with this for like, if I keep staying on this trend, I'm going to be here for like 3 hours. So I'm going to speed this up. Oh, okay, yeah, sorry, I had to respond to that text. Am I reviewing chapter 8? I'll be honest, Steven, I don't know what chapter 8 is. I don't know what these chapters are. Hold on, let me check what is chapter 8? Chapter 8 is... You know what? I'm gonna just do what Steven wants. I don't know. This is chapter 8, Steven. This is chapter 8. Alkenes. I guess we can skip to the more fun ones. We did the boring ones. Okay. Let's do the. Okay. Let's go on to. Okay. So we added things that we've added across an alkene so far. We've done H and H, we've done H and X, and in chemistry you can't really go far without water, so let's add water across an alkene. In other words, right, we can break this down into H and OH, and for those of you who don't know, OH is the alcohol, so in essence we're going to be making alcohol now. Yay! I know some of you would be happy about that. Some of you degenerates. Am I reviewing chapter 6? It's chapter 6. Cycloalkanes. Oh, this was the thing I was showing Anika how to do one day. But Anika doesn't take organic chemistry. For those of you who don't know, Anika doesn't take organic chemistry, but I was showing her how to do it. No, we won't be doing that. I don't have time for that, I guess. I know you're joking, okay? There are only 4 people watching this. I know that you're joking, Isabel. So, yeah, I know how to. I'm funny too. Okay, let's do this, right? Let's add water across an alkene. In other words, let's make alcohols. So, again, we run into 2 problems, okay? What if we want the anti-Markovnikov, anti-M, and what if we want the Markovnikov? So let's do the Markovnikov one first. Let's add the alcohol to the more substituted side. In this case, you're just going to be doing what we normally do, except water is not a good electrophile. It's an okay nucleophile, but that means it can't be a good electrophile. So we need a good electrophile. And what better electrophile is there than, well, there are a lot of better electrophiles. But let's take this monstrosity of an ion. This is called hydronium. And it's everywhere. It's in your body. It's in your drinking water. It's freaking everywhere. For those of you who are uninitiated, hydronium is literally what makes acid acid. Not acid, the thing you put on your tongue, but acid, as in hydrochloric acid. This is the H+. When you learn about pH, P means the power of, so negative log of the concentration of the hydrogen ion. It's referring to this. That's a detour into like Gen Chem and biology. We're not going to go into that. Although I love biology, maybe we'll talk a little bit about it. Maybe one day I'll just live stream myself talking about biology for an hour. I don't know if anyone would be interested in that. Leave a comment if you'd be interested in that. But here we have a decent electrophile. The negative charge will be placed on the oxygen, positive on the hydrogen. So we do know what we're moving. We're getting this hydrogen. And Stephen, I know for a fact you take organic chemistry. So what reaction is this? This is what kind of move is this where this alkene specifically takes a hydrogen? Okay, I'll check the chat in a few minutes, see if you got the answer. Right? So we're going to attack this hydrogen, and what we're going to end up with is CH3. The hydrogen will be on this side because you want the positive charge on a carbocation, and we end up with our good old friend. Look at this. This is water. Water is kind of thick as a molecule. I mean, I'm only sharing the whiteboard right now, but it's kind of thick, you know. It looks like that. Okay, and now that we have that, we got that going for us. Oh, let me actually keep up the water. Remember how I said that water is like a decent nucleophile? So it can perform this attack. It can now perform this attack over here to the electrophilic side of this alkene, and we get CH3, and now we have this water attached. Now the thing is that water is kind of a free spirit. Water enjoys being by itself. It doesn't like being bonded to other things. So it's going to do one of 2 things. It's either just going to flat out leave this molecule. This water does not like being attached. It's very upset about it. So it's going to either completely leave, but that's not really going to happen. We just had it attached, so why would it leave? or it's going to transform itself so it's no longer water. And remember how we said we're going to make an alcohol? We're going to make an OH? That means that this hydrogen is going to leave. This hydrogen's going to be like, okay, I'm out of here. This is not a good situation to be in. And we're going to end up with, well, let's remove the hydrogens. We're going to end up with this molecule. And what is this? What is this, you ask? Do I want to name this right now? I'm not going to name it, but you're going to end up with this molecule at the end of the day. Steven said B. This is not a multiple choice question. Nucleophilic attack, protonation. Yes, it's a proton transfer. So yes, protonation. Good job. If we want the anti-Markovnikov reaction, we have to do all kinds of shenanigans because we can't really do a free radical addition here. We have to do something called, okay, this is where organic chemistry gets its reputation for being a really tough class. We have to do something called oxymercuration, demercuration, and this monstrosity, I would not blame you for leaving the stream right now because I'm about to go over a very important reaction. Someone just joined as soon as I said that, so ignore everything I said. Let's say we have, I don't know, this one's more easy to visualize. If we have a ring, oh, the club is having budget problems right now. Oh, that might mean we have to end the stream early. Anyway, let's finish this. Long story short, this will get you your anti-Markovnikov addition of H and OH. And the way it's going to do that is you're going to have, let's say we have this alkene. Remember that this is an alkene right here. We have to use a series of reagents to get this step. The first is going to be, oh god, mercuric acetate, right? And I'm not going to draw this out, but this, in essence, the way this is going to work is it's going to try to attack this mercury. This nucleophile, this alkene, is going to try to attack the mercury. And so far, we've had the nucleophile attack things like, you know, it's attacked hydrogens. It's attacked, well, to be honest, we've only had it attack hydrogens for now. But hydrogen's really small. Hydrogen's the smallest atom. If you pull out your periodic tables, mercury is a big atom. It's big and it's very electron dense. Not electron dense, but it's very electron rich. And so if you try to attack mercury, it's not just going to follow like hydrogen. It's going to fight back. So, and you also have these acetate groups here. So you have this big ass metallic compound thingamajiggy, and in essence, if you try to attack the mercury, especially with the acetate, it's just going to attack back. Like it's going to fight back against you. So one of these oxaloacetate groups leaves. I think that's oxaloacetate. Someone, yes, oxaloacetate, and you're going to get a ring around it. Like this trips up a lot of people when they see it. And all we're going to do here is we're going to break the ring with water so we get the, oh wait, I'm a dumbass. This is not going to be, oh my gosh. Anyway, we're deleting this stream afterwards. Teehee, this was a meme. That was not the anti-addition of H2O. In essence, I don't know what I'm talking about either. That was to prevent rearrangement, right? So what I was trying to say there is, oh my god, I think I just messed up the whole. Let me read this message first. You can like look at this. Hold on. Okay, so yeah, I that was not 2 minutes. That was like 30 seconds. But anyway, so I said that that would prevent get you the anti-Markovnikov product. It wouldn't. What it would do though is if you have, I can't draw a fucking pentagon. What would happen is it would, this big ring that forms here would lock these bonds in place. And so from here you could control where your water, because remember we're adding water across the bond, right? That's going to control where it attacks. So it'll still attack on the Markovnikov side, but what's it going to do is prevent the carbocation from rearranging from one place to another. So that's what I meant to say, and I'm sorry for that. Oh, and so that's the first reagent you need to do that reaction. And then you'll need, what else do you need? You need water, obviously. And you need hydrogens to like fill up all the gaps. So I think we use BH4. I think I might be wrong, but this is a good source of hydrogens. Anyway, so if you do want the what do you do for the anti again? Yeah, thank you, Steve. NABH4. If you want the anti, you do the hydro. I don't want to say this word. Hydroboration oxidation. And based on this name, you can tell a lot about this reaction, such as it's boring because it has the name Borat in its name. Although Borat, I don't think Borat's a boring movie, but we're going to be using boron, this BH3 to do this reaction. And so it's going to be very similar to the oxymercuration, where you have a bigger atom allowing you to fight back and form a ring. So with BH3, what's going to happen is, so let's say we have our usual CH3, HCH3. I'm going to start using this example from now on. If we add BH3 to it, we get a nice ring. So this is going to attack the hydrogen here, right? And this boron's going to like fight back against it because it's bigger and has more electrons. So you're going to get this thing. So CH3, this should be on a... this is horrible. If you draw these reactions, like these specific drawings in this shape on your test, please don't. They're generally correct, but they're very messy. You're gonna get... It's not really a ring. Well, it is a ring. It's a square thing. It's gonna look something like this. These dashed lines are just to represent that whatever this boron is, it's attacking right back at the nucleophile. So now they're kind of like in a lock with one another. And what we're going to get from that is, I genuinely do not believe that any professor is ever going to make you do this whole step reaction. So just know that once you add this BH3, you add H2O2, NaOH, and water, and you will get your anti-Markovnikov substitution. Yay! Okay, and the reason I'm skipping this is because I'm 100% sure you will not need to know the exact arrows for this. If your professor makes you do that, you should report them for torture. I'm not going to draw that out for you. I'm sorry. And everything else is going to work this way too. So here, this one's just plain halogenation. What if you want your X on both sides? This one's pretty straightforward. You're going to have your like this. It's not really going to matter because there's no more you're adding the same thing to both ends, so your Markovnikov, anti-Markovnikov doesn't matter at all. You have your halogens, and the halogens are all pretty big. You know, your fluorine is a decently sized atom, but once you get to like bromine and then iodine is gigantic. The things you can do with iodine are incredible. When I was in high school, I had a project. All right, you know what? Screw this. Let's just talk about my life. When I was in high school, I had a science research experiment where we wanted to okay, so I grew plants, right? So we had like these little styrofoam cups. Styrofoam is white. Wait, hold on. Let me respond to this text really quickly. Okay. I don't know if anyone's still here. Y'all are still here. Oh, okay, so now y'all get to watch me tell a story. Okay, when I was in high school, we had this I had this science research project, right? It was my personal research project for our county science fair, and we had I was growing plants, and I wanted to see how carbon dioxide in the air impacts your nutrient content, right? Now, first off, there are a lot of nutrients. So technically, I don't know, from a health perspective, water is a nutrient, sugar is a nutrient, your vitamins, minerals. There are two more, fats and proteins. These are your 6 basic nutrients in health. But I focused on 4. And that was because I had ways to actually measure them. Actually, I focused on 2. I'm sorry, I messed up. Starch, which is just long chains of sugar, and vitamin C, also known as ascorbic acid. Ascorbic acid, and in part because these 2 had decently easy ways to measure concentration. If I wanted to do something like vitamin D, that's a lot harder to do. Maybe not even super possible in a lab, in a high school lab setting. Actually, maybe these weren't even really that possible because I got weird ass results from this. But so for those of you who don't know what how starches work, so this is glucose. All right, it's a hexagon, and when you start to chain up glucose molecules together, all right, this is a polysaccharide. And from here, you can get all kinds of polysaccharides, but when you chain glucose together, you get starch. And so I'm not going to draw hexagons. I'm just going to draw them as circles. Starch can form in 1 of 2 forms. If you have these long branching chains of starch, you have one form. I don't remember the name. I should know the name off the top of my head. What's the name for this thing? If you have branches like this going out, like that, we call this amylopectin. But if you have it in this nice helix rather than branching out, we call this amylose. And actually, at the end, your saliva has something called amylase, which breaks down amylose very well. So sometimes, I don't know if you've ever done this before. Maybe you should. But can take a Ritz cracker or something. I eat Ritz crackers a lot. Some of y'all will know this story. I'm not going to tell the full story. But if you just eat like a plain Ritz cracker and you just keep chewing it in your mouth, like chewing, munch, 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 and you let your saliva do a lot of digestion in it, you might start to taste it get a little bit sweeter. And that's because there's an enzyme in your saliva called amylase that's very good at breaking down sugars. Well, not very good. Its job is to break down sugar. So if you start chewing on it, you might start to taste the individual monomers of glucose break. Anyway, so that's one thing. It might be easier to detect with a saltine cracker because Ritz crackers have a lot of salt in them, and it might disguise the flavor. Saltines are pretty flavorless, if you ask me. Unsalted saltines, although is it really a saltine if it's unsalted? I don't know. But if you have something like, I don't know, let's just draw it like this. This is your amylose, right? One way you can detect whether or not this is in a solution, right? And that's what I wanted to see. I wanted to see how much starch there was in a sample of plant. So I crushed it up, right? All right, let me draw this out. Like I don't know, like grade A under A style, right? So there's like a mortar and pestle, right? This is like a, you know what I'm talking about, art people. You know what I'm talking about, mortar and pestle, right? Ritz crack. Hey, don't knock it until you try it, all right? So you have your mortar and pestle, right? I took the plant and I put a little bit in here and I would grind it up. And it's a lot harder than it looks because this is so small. You have to add a little bit of water. Although in hindsight, that was a really bad idea. Because it would have diluted the solution a bit. But if you make sure that when you add it to the graduated cylinder, that water is taken into account, I guess it wouldn't be that bad. Water doesn't actually digest starch very easily without some kind of enzyme, although it is soluble in it. Anyway, so you get this kind of, I'm going to have like a graduated cylinder here. You get this kind of solution in here, and in here you have your starch. But how much starch is in it? And so we can use a technique called spectrum phytometry to measure how much is in it. So you shine a light through it, in other words. And so the more stuff there is in the solution, the less light is going to pass through. But the clearer it is, all the light will pass through. So we can graph that relationship. It's a linear relationship. So on this axis, you're going to have the concentration, and on this axis, you're going to have the, I'm sorry, I flipped them around. This, you're going to have the absorbance of light, and here you're going to have the concentration of the substance. You can plot this out. It's a linear relationship, so it's represented by the equation y equals mx plus b. And from here, you can just use mx and b to figure out what your y, your concentration is. So, however, those of you who have done cooking know that cornstarch, potato starch, and wheat starch, which is just flour, they're clear, they're white. So if you put them in water, the solution is going to be white or clear, and that's literally useless if you do spectrophotometry, because white doesn't absorb any light. Black absorbs all light. So you want to make it colored. But the thing is, if you just add food coloring to solution, it's not going to indicate how much starch there is in it, right? You're just adding food coloring. So we need something that changes color upon reaction with starch, and that thing is the iodine. Actually, I think we want iodate, but I'm not sure. Let's just say iodine, right? So when this iodine reacts with starch, it's actually going to go into this helix, and here it forms like this complex. It's bonded to oxygen too, and it, as you can see by the color I chose, it becomes purple. So you're going to get a nice purplish color. Hang on, let me go through my Google Photos and see if I can find a good picture of it. I don't think I will, but I hope I don't, I'm not streaming my photos. Let's go down to, it would have been February 2019, maybe a bit before. Let's see. No, it would have been 2018. So 2 years ago. I have a picture of the iodine stock solution. So you can see. God, where is it? I don't think I have any pictures of it anymore. I think I deleted them. But I can show you what iodine's natural color is. Iodine's natural color is like this specific solution of. Oh, that's wrong link. So iodine's natural color is this. It's like it's closer to your orange. It's like an orange, dark orange color, right? But if you react it with starch, it turns into this purplish color. I don't have a picture of it right now, but in essence, that's what you're looking for. So I don't know. I actually didn't get to the reactions that will be relevant for this test, but I don't really care. This is normally what happens when studying, right? You derail yourself. Am I going to end it like that? Am I really going to? No, let's do one. Okay, no, let's do 3 problems from a previous version of this exam, just so that we can say we did something. Okay, is that good with everybody? I have an old exam 3. Does this have the answers? It does have the answers. Okay, this one looks sufficiently evil. So let's do... Actually, no, let's not do that one. Okay, let's do this one. Okay, I know this is just so that I can say we did something. Let's do this reaction where we convert, let me see, one ethene into one butane. Okay, so let's just draw these out to see what we're working with. F means two carbons involved, and ene means it's an alkene, so boom, 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 boom. Okay, and this one butane, so but means 4, so 4 carbons, and ine means alkyne. 1 means it's on the first carbon, so like this. And we don't need to draw the hydrogens, and I don't have the answers for this, so there's a very good chance I'm just not going to know how to do this. So y'all in the comments are going to have to help me out. How do you do this? There is an answer here, but it's marked wrong, so I don't think we're gonna rely on that. Let's check the chat if there's anything. Oh, bye, Isabel. Isabel has to go. Bye, Isabel. How do we do this? Shit. Oh, okay. This is how we're gonna do this. So first thing we're going to do is we're going to make this alkene into an alkyne. Get this out of the way. So the way we're going to do this is we're going to... Do I have you here? Yes, I do. We are going to... How do I do this? Yeah, let me think about this for a minute. How do we convert the alkene into an alkyne? Well, we could do... we can't do an... Oh, there's only one viewer. We can't do an elimination, can we? Can we? Okay, hold on. Let's try ethoxide. It's gonna attack you. Will it do that? I don't think... No. I don't know if this is going to happen. Okay, let me go through my notes and see if we have something, because I don't... My first instinct would be to do an elimination, but I don't think that's going to happen necessarily, because something tells me that if we do an elimination, it's going to... it's not going to react because this bond is not as polar as we'd like. So let's see if I can find something in my notes about turning an alkene into an alkyne. Yeah, it is E2. Yes, okay, so I was correct. We are going to do an E2. So I don't know how to do this. I think we do an E2. Wait, but the difference is... Okay, so we can do an E2, but the problem is there's no good leaving group, so the hydrogens are not good leaving groups. So we need to install leaving groups. Okay, let's write out our plan of attack over here let's do it in blue. First thing here is we can do E2, but we need leaving groups, right? And hydrogen is not a good leaving group. We want something that's good by itself. So the first thing that comes to mind is a halogen. So let's just do bromine. Bromine is... How are we going to do this? Well, okay, let's install... We need 2 bromines, actually. No, we only need 1. We only need 1. Because then we can do... Yeah, we're at an alkene, so we only need to do 1 E2 to get an alkane. So let's do... it's not going to matter which one we do, right? Okay, so let's try to do an addition like we did earlier in the stream when I still hadn't given up yet. Actually, was I ever really not giving up? Okay, so let's say HBr, right? Okay, let's try it. Again, like I said when I started this isn't like, a teaching live stream. This is me studying, so you should have anticipated this. Okay, so let's see if we do this, right? We're just gonna, let's just skip the mechanism. We already did this. We just have 2 sides, so it's not really gonna matter, right? Aha, yes. Okay, this can work now, I think. So now we can... Oh, we're gonna need another... We're going to need another bromine to get it to an alkene, because we have to do 2 E2s. So you know what? Instead of doing HBr, let's do Br2. Okay. I know we didn't really do this one, but let's do it anyway. We're gonna get. Yes, actually, this one would work better, because you're gonna get them on the anti-position. So yes, this would work better actually, because you're gonna get them opposite of one another, and so now you're going to be able to take any kind of nucleophile, a base rather, not nucleophile. I'm gonna use ethoxide, and we're gonna have two of them, and we're just gonna do 2 E2 reactions. So 1, 2, 3. And then the second one's gonna go here. So we're doing this reaction twice until we get carbon, carbon, carbon. Hydrogen, hydrogen. And to anyone who asks why we didn't just do the E2 here, again, it's because we didn't have a good leaving group. We had to install a bromine. But if we installed the bromine, then we'd go down to the alkane. So we would have needed 2 bromines anyway, so that's why we chose Br2. Yeah, there's something vaguely similar to this in my notes, but that's just the way we would do this. So that would be the first step. So now instead of ethene, we have ethyne, which is somewhere, and we're trying to get this thing. Let's just circle what we're trying to get. Well, the good news is we already have half of this down, so we have this side down. We're just trying to get this side here, and we can install this all as one group. That's what I'm thinking. But we'd have to get rid of this hydrogen and replace it with all of this. So why did we use OET? You can use any strong base, OET, OH. OET is just my favorite, ethoxide. But actually you can use OH minus. It's the same thing. Or OH minus. But we need 2 of them to do this. 2 moles to do it properly. So next up, we have to install this as a group. But hydrogen's not a good leaving group, and this group would not be very good. So, okay, if we are thinking about replacing one thing with another, we have to use a substitution reaction. But substitution requires a strong nucleophile. We don't have any of those. So we have to make this into a strong nucleophile. So let's take this thing here. Let's take this group here, because that's what we're installing. We're going to replace the hydrogen with that. We have CCH. So let's say we have a bromine here at this end. So we have an alkyl halide. So we have 1, 2, 3. We have 3 bromoethane. Or ethyl bromide if you want to use the common name. So from here, okay, we're almost there. But again, this is not a good leaving group. So this can do SN2. This is just not a good leaving group. So we would need to deprotonate it. Deprotonate this. We can do that. There's one thing that can deprotonate an alkyne, and that would be NaNH2. This can do it. So if we treat that with NaNH2, we get, see something really quickly here. We'll get, yes, we will get acetylide, which is exactly what we need for this. And so let me just check the mechanism one more time. Yes, so this is now a good leaving group, right? So we can use this to attack this whole thing, basically. Move this here, and you would end up with CCH234. Yep, this is it. Okay, that was quite a ride, but I'm assuming that we're going to see something like this on our test tomorrow. Let's do one more from this old test, I guess. Okay, let's do... Wait, this has been going on for an hour? According to my OBS? Okay, I'm going to end it after this problem. We're going to do one more problem. Let's say we take... Oh, mistake. Again, I'm taking this from this old test I found. Okay, so this one's actually one that we've done. I guess that's a nice way to end it with something we actually did today. Just making sure I get the molecule right. Okay, and I guess for just an additional problem, we're going to name it. That's a good practice. And for number 2, we're going to do the reaction, and we're adding HBr. So we actually did this reaction, but let's name this using our IUPAC rules. So let's do that in blue. 1, 2, 3, 4, 5. Number the carbons. I like to circle our functional groups and substituents. So we have a methyl here. That's 1 carbon. And we have our alkene. So I like to put the suffix "-ene". So let's do this. There are 5 carbon atoms. So we know we're working with pent. We know that there's an "-ene" here, so we can put the suffix here, "-ene", and it's on the 2nd carbon, so we can do pent-2-ene, alternatively 2-pentene. This is the same thing, but I like to do 2-pentene, and pent-2-ene rather, sorry. And then we have a methyl on carbon 2, so it's 2-methyl, and if we're going to be very... No, actually, we're done. This is it. It's 2-methyl 2-pentene or 2-methyl 2-pentene. Now for this over here, let's get rid of all of this. We have a... we did this already basically, so we're going to take this alkene. It's a nucleophile. It's going to attack this electrophilic hydrogen. Now the question arises, which side does the bromine attach to? Remember, we're going to have a carbocation wherever we go. So let's put the carbocation on the more substituted carbon, which would be this one. And the hydrogen can go here, although we don't even need to indicate it. It's a hydrogen. And then your negatively charged bromine, you're going to get a nucleophilic attack up here until you get this as your product. This is it. And I don't know, this is not on the test that I see in front of me, but what if there was a question on yours about the stereochemistry of this? In other words, you see how this carbon is, oh, this carbon is not chiral, but let's say that it was. So let's make it chiral now. Okay, now it's chiral. Is this chiral is it going to produce the R isomer or the S isomer, or configuration isomer? And the answer is it will produce both. And the reason for that is, remember that carbocations are empty p orbitals. So they're empty orbitals, so we can draw that out as this, right? these are empty spots for electrons to attack, which means that your bromine can attack either the top side or the bottom side. It can attack both. So if it attacks the top side, it will form one isomer. If it attacks the bottom, it'll form the other. Hard to tell with this one which one it will be without seeing which one's on the dash, which one's on a wedge. But you can control the stereochemistry of other reactions because you won't have necessarily this p orbital forming. You might have this empty p orbital. You might have something like I don't know. You know, you'll have specifically, like we saw with the first reaction we did with the hydrohalogenation. You know, you block one side from being attacked. So I think that's all we're going to do because acetylide and alkynide. I know what acetylide is. What's alkynide? What is alkynide? Huh. I don't know what that is. Alright. Alkynide is a terminal alkyne in which the terminal carbon is in the cell. Huh. I don't see. What's the difference between these? Oh, so acetylide is. So acetylide is a chemical formula in which M is a metal. The term is used loosely and can refer to substituted. Okay, so acetylide is. Let me clear the board, I guess. So acetylide is this thing, or rather, let's use R because it can be any group. R, H, R prime to show that you can have two different R's. But an alkynide, what's the difference? Alkynide ions. So the alkynide is the ion. So it would be if you had specifically something like this. That's my guess. It's based on what I see. I mean, yeah. Also called, if it was in this form, this is the form that's more common. This is called acetylide. Okay, I'm going to head out now. This is a live stream. I don't know how long it lasted, but we barely went through anything in the actual test material, but it's okay. Alright, I'm